Hey everyone, what's up? This is Karthik, and in this video we'll be discussing a problem based upon DP on trees. The problem comes from Codeforces, and I think this is a very interesting problem. Also, DP on trees has been a very hot topic for the viewers of the channel, I guess. Let me know in the comments if that's true. If you are enjoying DP on trees and you liked the series, it helped you, let me know in the comments. And we'll get started with this problem. I think this is a very interesting problem and it's considerably harder than the other 7, 8, 10 problems that we have done in the series. So you will get to learn a lot, I guess. Let's solve the problem. I found it very interesting. The problem is Appleman and tree, and it says that you are given with a tree, of course. So you're given with a tree having n number of nodes, and the edges format, everything is given in the input. Let's say now you have your tree. Each node of the tree is either black or white. Okay, so this could be black, this could be white, then this node might be black, white, black, something like that, right? All the nodes have some color, either black or white. The problem is asking you to find out the number of ways in which you could remove edges. So basically you are going to remove edges. Okay, if you remove one edge, the tree breaks down into two components, one component, two component. If you remove two edges, the tree breaks down into three components. So if let's say I remove this also, then one component, two component, and three component. So basically if you remove k plus 1 k edges, then your tree breaks down into k plus 1 components, right? So you're going to remove some edges of this tree, and if you remove k edges, it's obvious that the tree breaks down into k plus 1 components. Okay, imagine that the tree has exactly maybe what, let's say k plus 1 black nodes. Then you would like to find out the number of ways in which you could remove exactly k edges from the tree, so that each of the remaining k plus 1 component has exactly one black node. Okay, so remove k edges from the tree, given that the tree has k plus 1 black nodes. So remove k edges, the number of ways in which you could remove k edges, so that each component of the resulting tree, once you remove the edges, you are left with k plus 1 components, right? So that each component of the resulting tree has exactly one black node. Okay, exactly one black node. Hopefully the problem statement is clear to you, otherwise I'll remove this red gibberish that I've written and you could read it on your own. So you want exactly one black node in each component. Good. Let's see how we can do that. We need to find out the number of ways to remove edges. Before we actually move to the solution, we'll be reading the sample input. But I highly recommend that before you see me draw the tree from the sample input, you read this input format. I really did not like the input format. The format that they have given is a bit hard to understand, but I know you guys will understand it by going through it once. Just pause your video, read what's written, and then we'll solve for input example 1. Okay, so the tree in this example has 3 nodes, and node number 0 is connected to node number 1, and node number 0 is also connected to node number 2. Now the colors of these nodes are, node number 0 is white and node number 1 and 2 are black. From this and this, this tree comes out. Okay, so now you have this tree. You want to find out, since it has like 2 black nodes, you would like to find out in how many ways can you remove edges, so that the components, each of the component of the tree, of the resulting tree after removing the edges, has exactly one black node. Now I can either remove this edge. In that case, I'm left with one component and two component, and you can see that each of these components has exactly one black node, right? Here this one and here this one. So this is a valid way of removing edges. So one way for this, and if you remove this, the other edge, this one, then you're left with one component and two component, and you can see that this is also a valid way. So you have overall 2 ways, and that's the output. Now I'm not going to take larger examples, but hopefully the idea is clear. If it is not, I recommend that you read the problem again. Okay, also I've already tried out this problem. However, the code I wrote was a bit complicated, and I'll be writing the code again, but to save time, I'll just you know what, I'll skip the coding part anyway, but I'll be doing the code walkthrough, that's for sure. So you don't need to worry about something not getting clear. I'll make sure that everything is clear, because if it's not clear, then what's the use of these videos? Now let's understand the problem more graphically, right? You have this kind of tree, Yeah, trees look like this only. It's not a binary tree, it could be like any number of child for a particular node. And even though the problem does not say that the tree is rooted, I would still root it at any arbitrary node without loss of generality. So let me root the tree at node number 0. So let's say this is the root of the tree. And now you can view the tree from this way. Now the tree has a root. And these are the child nodes of this node. Okay. How does that help? Now if you think about it, the problem is basically saying that you break this tree into some components, and after breaking down, the tree should look something like this: 1 component, 2 component, 3 component, 4. Okay, these nodes will break down into such pieces of basically a lot of trees. This one tree breaks down into a lot of more trees, and each of these components, after breaking down or removing these edges, has exactly one black node. So there might be any number of white nodes in here, but there is exactly one black node. One black node, black, black, black. Okay, you may have 0 white nodes in a particular component or 1000 white nodes in a particular component, but overall each component is going to have exactly one black node. That's the requirement, right? You would like to break this tree down in this kind of manner. Good. Let's think about it more, how we can actually even approach this problem. It seems a bit hard on the face of it. In fact, to me it felt a bit unsolvable for the first maybe few minutes or maybe 1 hour, whatever, but overall the solution is very, very elegant. So now this is my tree and this is the root of the tree. This root node has some child nodes, and each of the child node has its entire own subtree. So let's, for example, say take this to be our tree. This root has 3 child nodes and each of them have their own entire subtrees. Now the root can either be black or white. For now I consider the root to be black. Okay, we'll consider the other scenario as well when the root is white, but for now let's think that the root is black and try to solve the problem. Our problem is to break down this tree into components so that each component has exactly one black node. Now if the root is black, I can definitely make this one component. This entire root is one node and one component, and then I'll be left with these 3 subtrees, and I would like to break them down into components so that each component has exactly one black node. So for this subtree, I would like to break it down into components so that each component has exactly one black node. And similarly for this one, similarly for this one. So the problem that I wanted to solve on the entire tree, by doing this, breaks down into solving the same problem but for smaller subtrees. And if you were able to find out the number of ways in which you could break this subtree down into components so that each component has exactly one black node, similarly for this and this, let's call that W1, W2. There are W2 ways of breaking this subtree down into components, blah 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 blah, and W3. Okay. Then I could use one of the W1 ways regardless of which way I break down these 2 subtrees in. Same way I could choose any way of breaking down this subtree regardless of what I choose, what way of breaking down I choose here and here. And overall if you see that, you will get okay W1 into W2 into W3 ways of breaking down this entire tree so that this is one of the components. Okay, good. This is definitely going to be included in my answer for sure. Right, these number of ways are definitely there, but can there be more ways? Yes, there can be more ways. Now I chose this to be the first component. This component could have been larger, right? Because this is a black node, that's good. Now no more black node is allowed in this component, but white nodes are allowed in this component. So if, for example, if this was a white node, I could have happily included it in this particular component here, shifted it to this component, and then for the remaining portion, I would like to break that portion down into components so that each component has exactly one black node. I could take some white nodes from this portion also and some white nodes from this portion also. Also, I cannot just take one white node, I can probably take more, right? I can probably take these 2 white nodes if these are white. I can take these and I can take more. So it's basically that some white component portion you can take from here, and that component should definitely include the root, and you can include it with this guy, root of this subtree, this one, and you can include that particular white component or component consisting only of white nodes into this, right? because you cannot take any black node from here, because then there will be two black nodes in this component, which is undesirable. We want only exactly one black node to be in a component. So if you think about it, if I knew, let's think about this, let's zoom this portion out. If I think about this particular subtree, the subtree number 1, this one, if I was able to break it down into one white component, and this white component definitely contains the root of the subtree, white component meaning that all nodes in this component are white, and then the remaining components should contain exactly one black node. If I was able to find out the number of ways in which I could do this, the number of ways in which I could break down the tree so that the component containing the root of the subtree has all white nodes and the remaining components have black nodes, exactly one black node, the remaining components. If I could find out the number of ways of doing that, I could probably include these white nodes with the root. And for the remaining, of course, they are breaking down nicely. But I could include this white component containing the root and all white nodes along with this particular root here. Similarly for this one and this one. This gives you a good intuition of what solution we are going to go to. Okay, with this intuition, let's define some DP. So let me define DP of black of u and DP of white of u. Okay, so DP of black of u basically means for the subtree rooted at node u, for the subtree rooted at node number u, what are the number of ways in which you could break down this subtree? Ways to break, sorry for the handwriting, ways to break subtree, oh god, I'm not going to write this completely, rooted at node u into components so that each component has exactly one black node. Okay, this is DP of black of u. And if you think about it, the DP of black of root is going to be your final answer, because that's the problem, right? What are the number of ways to break down your subtree rooted at the root, which is the, of course, the entire tree, into components so that each component has exactly one black node. This is what DP of black defines. Now I'll define DP of white also. What is DP of white of u? It's again the number of ways to break down the subtree rooted at node u into components such that the component that contains node u, the component containing node u has all white nodes. The component containing node u has all white nodes and the rest of the components have exactly one black node. Okay, with these two definitions, we'll be able to come to a solution. So let's solve it for the root now. Hopefully these two are clear. If you have any doubt, I recommend that you pause the video here, think about what I'm trying to say, write it on pen and paper. It's a bit complicated, but once you understand, it will be very elegant. The solution is good. And if you still have any doubts, feel free to ask in the comments. I'm very active in the comment section. I'll definitely reply back. Okay, so let's remove this part and come up with a recurrence. So this is DP of black of some node u. Consider u is black. Okay, we'll think of what happens when u is white, but for now let's consider u is black. We know that I can obviously assume it to be one component, this black one. So I don't take any white node from here, I don't take any white node from here, and I don't take any white node from here. And you see that your answer overall becomes product DP of black Ci. Basically solve the problem for this subtree rooted at the child of u, solve it for this, multiply the number of ways for each of them independently, and you'll get it for the tree. Product over all child nodes of u, Ci, or see where Ci is a child of u. I'm not writing the full statement. Okay, this part is clear, but we saw that we can probably take out some white nodes from here and put them here, isn't it? Similarly, some white nodes from here. So how many white nodes do I take? Okay, Now if I take some white nodes from here, it's basically going to be one white component from here, some white component, right, that definitely contains the root, some white component. You're going to take that, include it with this guy, and the rest of your tree breaks down into components. This rest portion of the tree should break down into components so that each component has exactly one black node. And by definition, the number of ways in which you could come up with one white component here and then break down this portion into ways so that, oh, I'm not going to speak that again. Okay, I'll have to. So the number of ways in which basically you take one white component and then the remaining components automatically break down into one components having exactly one black node. The first node has all white nodes, and that is going to be included here, is basically nothing but dp of white of this node. And I can take some white portion from here. There are basically going to be dp of white things to do, dp of white of ci. These are the different ways when I take some portion from here included with you of breaking this portion down. Similarly, I could go ahead and pick some nodes from here and pick some nodes from here. It's going to be product dp of white of ci, where ci is a child of u. Overall, simplifying this thing, I'll explain it once again, but I do hope that you got the idea. So if you think about it, you will be able to solve it on your own. Oh. Where ci is a child of u. This is going to be a recurrence for dp of black of u. Now this particular portion, which might be a bit confusing to you guys, but overall it means is that some white portion, you take it because you broke this particular subtree down here into one white portion and the rest as black portions. So you're taking this white portion, including it with this one, and this is the number of ways of doing that, dp of white of ci. And you could basically do that for each of the subtree independently, and then you'll use one of the ways here, you'll use one of those ways here, and the ways here will be dp of white of c1, dp of white of c2. It's basically the same reason why we included this and multiplied them. The same reason for this one is going to be product over, and this thing simplifies to product of sum of dp white ci and dp black ci. Hopefully this is somewhat clear to you, but you can obviously always ask me in comments if you have any doubt. This is dp of black for u. Now we also need to think about dp of white of u. Now since u is black node and dp of white basically means that what are the number of ways to break down blah blah blah, so that the component containing the root of the subtree is has all white nodes. Since u itself is black, the ways will be 0. So dp of white of u is going to be 0 since u is black. Good. Now let's try to solve the problem when dp of black of u when u is white. It's something like this. U is white. Now in this particular case, you cannot consider u alone to be one component. You need some black nodes. You definitely need some black nodes. Now those black nodes can come from this portion. They might come from this portion or this portion, but you need to get one black node for sure. Now if you get one black node from this portion, let's say that I'm going to get one black node from this portion. Okay, then I will be first of all breaking, let's call this C2, the second child of u. Then I will be breaking this subtree rooted at C2 down into components so that blah blah blah, right? So that each component has exactly one black node. And the first node that contains C2 itself, I can probably include it with u. And then that is one way of getting a component related with u, and that this particular component containing u becomes black, right? That is one way. And you could basically take either of these dp of black C2 ways. You could go ahead with any of these, and whatever the first component is, you include u with that. For the remaining these two guys, either you do nothing about them, you just forget about them, and in that case you'll be breaking this down and the ways of doing that will be dp of black of c1, dp of black of c3, and overall these things will multiply with each other to give you total ways. So that's good. This term is still there, product of ci of all u, ci, where ci is a child of u. Yep, this term is still there. Basically just take this as one component, break these three down and put u in any of the components here. I either put it here or put it here or put it there. Now let's just write it a bit more concrete. Okay, let's get a bit more concrete about this stuff instead of just randomly writing these terms down. One way is that you take some black portion from here included in this component, some component that has one black node, some this portion you include it here. Doing that is basically dp of black of c1. Okay, these are the number of ways in which you could take one black component, a component that has one black node, exactly one black node, include it here, right? What about the remaining two people? Either you do not take anything, right? Either you don't take anything from here, don't take anything from here. That is one possibility. Okay, so for this one I can either go ahead and not take anything from here and then break this tree down here in dp of black of c2 ways, right? Because I already have one black node here, so I don't need any more black nodes here. I took the black node using this component of c1. That is one possibility, that you can just not take anything from here and break this portion down in dp of black of c2 ways. The other possibility is that you break it down into dp of white of c2 ways and then you take the white portion here, right? You take the white portion here. So overall these two possibilities, both of them do exist and you can go ahead and take any of these. So it's going to be dp of black of c1 because this is going to give you a black node. This is obviously going to be dp of black of c1. Now you can either choose not to take any node from this portion from c2, right? You can choose not to take anything from here. Not taking anything from here gives you dp of black of c2 ways of breaking this component down. dp of black of c2 ways of breaking this component down. But if you want to take some white nodes from here, then you will be okay, I'll break this tree down into components so that the first component or the component containing c2 has white nodes, and you can take those white nodes and put them here. So you have another dp of white of c2 ways. Thirdly, for this one also, either don't take anything from this portion or you take some white nodes and put them here. Because black you have already taken, you can no longer take anything, any black node from here. You can only take white nodes or no nodes. So if you do not take any nodes, then the ways of breaking this down is dp black c3. But if you do take some white nodes, then okay, you will have this much ways of taking white nodes. So this is one possibility when you go and pick your black node from c1 or from this portion. But you could have taken your black node from this portion as well. In that particular case, you would have had dp of black of c1 plus dp of white of c1 into this thing would have become only dp of black of c2 because you are taking black nodes from here and not it's basically you're taking black nodes from here and it's not possible to leave this out. The third case would have stayed the same. So overall, this recurrence was the case when I was taking my black node and for this component from this subtree. You will be writing similar portion if you take the black node from this portion, or if you get your black node from this portion, you will get similar recurrences. Overall, it becomes something like this. U is white. Assume that U has n number of children, small n number of child nodes. Then for each child you will try, okay, I am taking black nodes from child number I am taking black nodes from this child. For the remaining you will have both the possibilities as discussed, and you will be doing this for each and every of the n children, right? And you will get your recurrences like this. One time you will have dp of b c1 into dp of black C2 plus dp of white C2 into so on till dp of black Cn plus dp of white Cn. Next time you will have dp of black C1 plus dp of white C1 into dp of black C2 into these things. And let me simplify this. Finally what it becomes is that product of LW I minus 1, sorry, not product, sum of LW I minus 1 multiplied by, I am taking the black nodes from the ith node for now, so dp of black of the ith node and RW of I plus 1. This LW I minus 1 and RW I plus 1 is basically the a prefix and a suffix. LW I minus 1 means this term dp of B C1 plus dp of W C1 into dp of B C2 plus dp of W C2 into so on till I minus 1. So if I parameterize it, it becomes product of let me write this j goes from the first child till the I minus 1th child, and this will be LW I minus 1, and similarly RW I plus 1 would be j would start going from I plus 1 till n, the nth child. So j equal to I plus 1 till n. This portion simply means that I am taking my black nodes from the ith child. The black component for the root u comes from the ith child, and for the remaining you have both the possibilities, so you just take a prefix and a suffix. This thing breaks down into this final recurrence, and this is exactly what I've implemented and I'll be showing you in code. I think we left out one last thing. How do you calculate dp of white of u maybe? So for dp of white of u is already white, and you can go ahead and break the remaining nodes, break the remaining portions into black components, and you will have one white component and the remaining all rest would be black components. The other way is that you take this white and then you take some white nodes from here, some white nodes from here, some white nodes from here, include it here. So overall it's basically going to be summation of, it's basically going to be LW n. You can think about it, it's very straightforward. Okay, let's go to the code so that things become more clear to you. Yeah, we should not waste more time. Let's move to the code. The code is a bit messy, but you'll be able to understand it. Everything is the same as discussed in the explanation. Okay. So this vector tree holds my tree. This black color basically says whether node u is black or not. So black color at u equal to true means u is black, otherwise white. dp at white, dp at black as discussed. This solve function will solve the problem, obviously. Okay, the solve function is a bit too long, but we'll break it down into portions and then discuss. Let's discuss the first portion. So as soon as you come to the root, you'll be like, okay, before I solve the problem for the root, I need to solve it for the child of the root, right? The problem should be solved for easier portions before you actually solve it for the root. You should have the answers for these nodes. So okay, before you solve for the root, solve it for all the child nodes. Once you're done solving for the child nodes, these are solved, you move ahead. Okay, so moving ahead, if your root is black, dp of white automatically becomes 0, because there is no way that you can have a component consisting of only white nodes that also contains the root, because root itself is black. So dp of white is automatically 0, no problem with that. Now I am marking my black components as 1 and using the recurrence which we discussed previously. Let me go back. Never mind. Yep, basically since u is black, I can consider it as one component and then break these portions down in dp of white ways for each child, or I can take some white nodes from here and then break it down into black portion. So it's overall for each of the child subtree of you have two options. Either you don't take any white nodes from them and break the particular subtree down in dp black child ways, or you take some white component from the child subtree and include it with the black node u here, and for that you have dp of white of child ways. Overall, for each of these you have independently these many ways. You multiply them together for every child and you get your answer, dp black root equal to black components. This is easy. Let's move to the second portion, when you're a bit harder to implement portion when your node is white. I know that there are better ways to implement it, but forgive me for now. So this portion, when your node, the root or node u is white, this guy is white. If this is a what do you call leaf node, in that case, since u is white, there is no way of breaking one node that is white into components that each component has exactly one black node, because this itself is white, so it's not possible. dp of black is 0. dp of white of this guy, if it's a leaf node, then it's basically like the first component is containing one white node, that is good, and the remaining components, since there is no component, I can just assume that those components also have exactly one black node, but they are non-existent anyway. So dp of white of root is 1 for a leaf node. Good. Now I'll be building those pref and suf. Pref is basically LWI, and you can see just for every child I've taken the black and white value of that node or that child and multiplied them together to get LWI. This guy is the ith node, this guy is the nth node, this is the root, and then LWI would basically mean LWI minus 1 would mean this portion, RWI plus 1 would mean this portion, and it's basically pref and suf. Okay. Where are my recurrences now? So this is the recurrence. I'm trying to find out dp of black. dp of white is simply LW of n, right? And for dp of black, I'm like, okay, I'll take the black portion from the child number maybe I, and I'll take LW of I minus 1 because for these nodes I have both the possibilities: don't take anything and break down into black ways, or break down into white ways and take the white component included with you. So left LW of I minus 1 is taken from this, RW of I plus 1 is taken from here, and the dp of black of child, this node, and you just try it out for every child and you are done. Here dp of black is calculated, and this gives you a nice AC. We are done. Hopefully guys you liked this video. I know it's a bit complicated problem, but if you have any doubts you can ask me in the comments. I would be very happy to show accepted verdict, because I did get happy. So yeah, make sure that you like, share and subscribe, and I'll see you in the next video. Bye.